The gold in your wedding ring was forged in one of the most violent events in the universe, and our moon exists because a Mars-sized object slammed into Earth billions of years ago at over 25,000 miles per hour. Space isn't an empty vacuum. It's filled with objects in constant motion, from tiny dust particles to entire galaxies, all traveling at incredible speeds. When these objects collide, the outcome depends on their size, speed, and composition. A small, fast object can pack more punch than a larger, slower one, and colliding with gas differs greatly from hitting solid rock. Gravity constantly pulls objects together, and while some simply orbit each other, many collide in dramatic fashion. Micrometeoroids are tiny space particles, often smaller than a grain of sand, but they travel at speeds up to 157,000 miles per hour, far faster than a bullet's 1,700 miles per hour. Despite their size, these tiny objects can pack the punch of a hand grenade, making them a serious concern for astronauts and satellites. This is a solar panel on the International Space Station that was hit by a micrometeoroid. NASA tracks thousands of pieces of space debris to protect the ISS, and spacesuits have layers designed to protect astronauts from these high-speed particles. On airless worlds like the Moon, there's nothing to slow them down, which is why its surface is covered in craters. Over time, the Moon's surface is constantly reshaped by these impacts, and even the Apollo footprints will eventually be erased. But what if the impactor is much larger, large enough to threaten an entire planet? About 66 million years ago, an asteroid about 6 miles wide struck the Yucatan Peninsula in Mexico, releasing energy equivalent to 10 billion Hiroshima bombs. The impact vaporized the asteroid and tons of Earth's crust, causing global wildfires, tsunamis, and years of darkness, wiping out 75% of Earth's species, including the dinosaurs. Scientists confirmed the impact site, the Chicxulub crater, by finding iridium, a rare element on Earth but common in asteroids. But you don't need a dinosaur killer to create dramatic effects. In 2013, a 20-meter meteor exploded over Chelyabinsk, Russia, injuring 1,500 people and damaging 7,200 buildings across 6 cities. The effects of an impact depend on the asteroid's size, angle, and composition. Rocky asteroids penetrate deeper than loosely bound comets. Smaller impacts can create beautiful displays instead of disasters. When Earth passes through debris left behind by comets, we experience meteor showers, streaks of light from small particles burning up in our atmosphere. In 1994, astronomers witnessed comet Shoemaker-Levy 9 fragments collide with Jupiter, leaving Earth-sized scars. Jupiter's strong gravity acts as a cosmic shield, capturing many comets and asteroids that might otherwise threaten Earth. But what about truly catastrophic collisions? The kind that don't just create craters, but can create entire worlds. The early solar system was much more chaotic than today, with dozens of planet-sized objects orbiting the Sun on unstable paths, setting the stage for massive collisions. About 4.5 billion years ago, a Mars-sized body named Theia collided with the young Earth. The collision was so violent that both Theia and much of Earth's outer layers were vaporized and ejected, creating a molten Earth. Over time, this debris cooled and formed the Moon. This theory, known as the giant impact hypothesis, explains why the Moon's composition is similar to Earth's crust, but different from its core. Mercury also has a collision mystery, as its large iron core may have resulted from a massive impact that stripped away much of its crust and mantle. And then Uranus, with its extreme tilt, likely experienced massive impacts that knocked it onto its side. These planetary collisions were not rare, but part of a period called the Late Heavy Bombardment, when massive impacts were common as planets settled into their orbits. Fortunately, our solar system has since settled, and catastrophic collisions are now extremely unlikely. But what about more dramatic mergers, such as stars? Over half of all stars in our galaxy are part of binary or multiple star systems, where two or more stars orbit a common center of gravity. These systems can remain stable for billions of years, but not always. As stars age, they expand dramatically. A star like our Sun will eventually become a red giant, growing to hundreds of times its current size, and in binary systems, this expansion can lead to interactions between the stars. One star may pull material from its companion, forming an accretion disk. This cosmic vampirism can trigger a nova, a thermonuclear explosion that temporarily increases a star's brightness by thousands of times. In some cases, the stars spiral toward each other due to orbital energy loss, eventually merging into a more massive star with unique properties, such as unusual rotation rates, magnetic fields, or chemical compositions. Our Sun will eventually expand into a red giant, likely engulfing Mercury and Venus. Earth may narrowly escape but would still have its oceans and atmosphere vaporized by the intense heat. But what about stars that have already died? It turns out that stellar corpses can create some of the most energetic collisions in the universe. When stars like our Sun die, they shed their outer layers, leaving behind a dense core called a white dwarf. These remnants pack the mass of a star into a volume the size of Earth. A teaspoonful of a white dwarf would weigh about 15 tons on Earth, similar to compressing a cruise ship into a sugar cube. White dwarfs often exist in binary systems, where they can pull material from a companion star. If the white dwarf exceeds a strict mass limit, about 1.4 times the mass of the Sun, known as the Chandrasekhar limit, it detonates in a Type 1a supernova. This explosion is so bright it can outshine an entire galaxy, destroying the white dwarf and blasting material into space at thousands of miles per second. Type 1a supernovae are remarkably consistent in brightness, making them ideal standard candles for measuring vast cosmic distances. In the 1990s, astronomers used these explosions to discover that the universe's expansion is accelerating, driven by dark energy. This discovery earned the 2011 Nobel Prize in Physics. These supernovae also create elements like calcium, iron, and oxygen, which eventually become part of new stars, planets, and even life on Earth. Neutron stars, on the other hand, are even more extreme than white dwarfs and can create some of the most exotic collisions in the cosmos. When a massive star dies, it can collapse into a neutron star, an object so dense that a teaspoonful would weigh 1 billion tons, equivalent to Mount Everest compressed into something smaller than a grain of sand. Like white dwarfs, neutron stars often exist in binary systems, orbiting each other. As they do, they emit gravitational waves, ripples in the fabric of space-time, causing them to spiral closer together. Over billions of years, their surfaces distort under each other's gravity. When they finally collide, it results in a kilonova, an explosion 1,000 times more powerful than a regular nova. In 2017, scientists detected both gravitational waves and light from such a collision, confirming Einstein's century-old prediction and marking a new era in astronomy. Scientists now believe most elements heavier than iron are formed in these rare and spectacular events. But there's one collision even more powerful than merging neutron stars. Black holes, the ultimate cosmic extreme, are so dense that nothing can escape their gravity. Like neutron stars, orbiting black holes emit gravitational waves, causing them to spiral closer together. The waves from black hole mergers are much stronger, detectable across billions of light years. In 2015, LIGO detected gravitational waves from a merger of two black holes, each about 30 times the mass of the Sun, 1.3 billion light-years away. In their final moments, they released more energy than all the stars in the observable universe combined, but only in gravitational waves, not light. As the black holes approach, they orbit faster, reaching speeds over half the speed of light. In the final moments, they orbit hundreds of times per second before merging. The merger occurs when their event horizons touch and combine, forming a larger black hole with new properties and releasing a huge burst of gravitational energy. A typical black hole merger releases more energy in its final second than our Sun will emit over its entire 10 billion year lifetime. Despite this, the energy is only detectable through gravitational waves, as conventional telescopes can't observe it. After the collision, the newly formed black hole wobbles briefly before settling into a stable state. These ring-down vibrations also produce gravitational waves, offering crucial information about the black hole's properties. But what about whole galaxies? Galaxies contain hundreds of billions of stars, vast clouds of gas and dust, and supermassive black holes at their centers. When galaxies collide, it's a slow-motion cosmic spectacle that can take hundreds of millions of years. The Hubble Space Telescope has captured stunning images of galaxies in various stages of collision, including the antenna galaxies, the mice galaxies, and the whirlpool galaxy. Unlike other collisions, individual stars and merging galaxies rarely collide due to the vast distances between them. It's like two swarms of bees mixing, but the bees themselves rarely collide. However, gas and dust clouds within galaxies do collide, creating shock waves that trigger star formation in a process called a starburst, lighting up the galaxies with the blue glow of newly formed stars. At the center of this cosmic dance, the supermassive black holes from each galaxy begin to spiral toward each other, a process that can take billions of years. Our Milky Way is on a collision course with the Andromeda Galaxy, and in about 4.5 billion years, they will begin to merge. While the Sun will likely survive, it may end up in a completely different region of the resulting galaxy. In a universe defined by constant change, collisions aren't accidents, they're essential. They're how the cosmos builds complexity, creates new elements, and ultimately made it possible for us to exist. If you enjoyed this cosmic journey, hit the like button and subscribe for more videos that explore the wonders of our universe.